Now let us talk about the negative integer representation. Remember, like all the discussion we did so far, we talked about a positive number or unsigned, if you want to think programmatically. We talked about unsigned integer representation. Okay, there is nothing signed associated with that. All right, so now let's see how can we represent a negative integer in electronic computing system, that especially that uses this binary number system to represent any value inside it. So we had different methods and in older days. Okay, of course the problem is there is no negative sign in electronic computing world. So what do you do? One way would be use a sign and magnitude representation of binary numbers using one of the bit as a sign bit. Okay, it has couple of disputes and problem with that concept. So what it's trying to say is that, okay, I have 8 bit, use one of the bit as a 7 bit. First of all, that's one of the things, this waste of bit. That's a different thing. But thing is that where we want to put that sign bit, is it at the MSB bit we want to do it as a sign, or the LSB bit? Both has a pros and cons from digital circuit perspective and circuit complexity perspective and stuff like that. Now may need an extra step to sign magnitude arithmetic logic unit to handle them and determine the sign of the result. And one of the another interesting things in that system is we have two zeros, like positive 0 and negative 0. Like let's say in a number system, we are trying to assign the last bit or MSB bit as my sign bit. Okay, if it is 0, it's a positive. If it is a 1, it's a negative. Okay, first of all, we are sacrificing the range, right, of the system a little bit. And then if imagine we have a pattern 0, all 0, 0, 0, 0, 0, 0, and then we have a pattern 1, 0, 0, 0, 0. In that case, you will have a positive 0 and a negative 0. What does it mean? How the software will handle it? And so many different question comes up with this approach, right? So what has been done, and now it is this is the way, the only way every computing system in the whole world represent numbers, okay, with a negative, both negative and positive way. Okay, so here what we are saying, first of all, this number system is called 2's complement form of representing any positive binary numbers and negative binary numbers as well. So this number system, the proposed system, is named as 2's complement number system, and it can represent positive and negative, both of them, in a similar fashion. And also it doesn't have that positive negative 0 approach. So what it says is this: any positive binary number with a has a leading 0. Okay, so if some bit pattern has leading zeros, right, it's not only this last position, but it has like this guy has all leading 0, this guy has leading 3 zeros, this guy has leading 2 zeros, and this guy has leading 1 0. Okay, so these are all my positive number, and any binary sequence or bit sequence has leading 1, they are negative. Okay, so this is leading by 1 bit, and then this is leading by 2 bit, this is leading by 3 bit, this is leading by 4 bit, and so on and so forth. So these are negative numbers values. So remember, like from this approach where only we are focusing on the most significant bit, whether this is 0 or 1, saying that they are positive or negative, in this system it is saying that it is not only this most significant bit position, but if they're all leading zeros or all leading ones, they are representing either positive or negative number. Okay, that is the first groundwork. Second is this. So if we see the positive bit pattern, okay, so we have the most value out of this for the 4 bits is this 0 1 1 1, which is like 7 in decimal. So after this bit pattern, the next unique bit pattern becomes 1 0 0 0. So this is a negative, and that is -8. Okay, that is -8 for 4 bit. And then next bit pattern, which is 1 0 0 1, it is -7. So we, okay, and 1 0 1 0 is -6, -5, and ultimately 1 1 1 1 is -1. So recall, with this approach, okay, with this approach, right, with this approach, I would say this bit pattern would represent a -0, right? This bit pattern would be positive 0. This would be -1, this will be -2, this will be -3, and this will be like -7. But 2's complement is proposing that this bit pattern to be called as -7. Right? This is a proposal. Like we are building up these representation and convention of saying what we say what. Okay, so how do we first of all compute what the corresponding decimal value? So we know what is the most negative value we can represent, which is the least value perspective. What is the least value we can represent with this 4 bit, which is -8, right? And then we take the, let's say for example 1 0 1 1. Okay, so we know this least value we represent is -8. Then to determine what this 4 bit pattern represent, what we do, we look at this 3 bit pattern. Okay, this is just an unsigned value of that. This unsigned value of this 0 1 1 is 3, right? Then we add that on top of -8. Okay, so if you do -8 plus 3, you get -5. If you do -8 plus 1, -7. -8 plus 2, because this is 0 1 0, which represent 2, that becomes -6. So this is how we can kind of tell that this specific bit pattern represent what. Okay, so and one more thing, very important. All right, so for a 2's complement number system, one must specify how many bit we are talking of. Is it a 4 bit 2's complement, or is it a 8 bit or 6 bit or 7 bit? No matter what, it can be like any number of bit, but that number of bit must be specified. Otherwise, it doesn't make sense actually. Just, okay, I tell you, okay, convert like 26 or -26 into 2's complement. That doesn't really make sense. We'll see that in next one or two example. But point is that if such problem comes in from converting the decimal value to an binary value in 2's complement form, one must specify how many bits we are talking about. Are we talking about a 4 bit 2's complement, or are we talking about 8 bit complement? Reverse is also true. If we are given with a binary bit pattern and say that convert it into the corresponding decimal, we must say that this binary bit pattern is of 2's complement of 4 bit or 8 bit or 16 bit. Okay, otherwise we can possibly infer that the bit pattern number of bit is that number of bit pattern is given, like we can like manually count number of bits there in the given problem and assume that, but that's not kind of right way to do or right way to formulate a question. Okay, so a question must specify as number of bits for the 2's complement form. There are advantage with this formation. First of all, it is very easy to convert a value from its positive to negative, corresponding negative values. circuit wise, logic circuit wise, we'll see it later in the semester. uh, Towards the end, we'll see that how that logic circuit is much ease up. This also opens up a scope for making addition circuitry reusage for subtraction purpose. We'll also see that in the towards the end of the semester. And essentially it actually ease up hardware engineering effort to do computation inside electronic computer. Okay, so you need to understand this number system very carefully, and this is very important. All right, so let's take an example. Let's say I want to do 160 base to convert it to 8-bit 2's complement bit pattern form. Okay, 2's complement binary form. We know, like, we put the indices 0 to 7, LSB, MSB, the decimal weight we put, we know how to convert. We start with, okay, 28, we place a 1 here and the subtraction to this, and ultimately we come down to a pattern of 1 0 1 0 0 1 0 0. Answer is 1 0 1 0 0 0, etc. The funny part is this is wrong, absolutely wrong, because see, we are talking about 8-bit 2's complement, and if a bit pattern is leading with 1, it has a negative value. It represents a negative value. It's not a positive value. So we are talking of converting 160 with 8-bit 2's complement, and to do that, what we are kind of doing is the pattern we are arriving, whatever method we learned so far, which is represent a negative number in 2's complement, right, by definition. So it is now important to look at the range of n-bit 2's complement binary number. So it is formulated as -2 to the power n minus 1 to 2 to the power n minus 1 minus 1. So that means if I am talking about the 8-bit, my range will become -2 to the power 7, which is -128, and 2 to the power n minus 1, which is 2 to the power 7 minus 1, which is 127. So 8-bit 2's complement range is -128 to positive 127. That means I have been given a value which falls out of the range of this 8-bit 2's complement binary form. I cannot convert it. It is not possible to represent 160 with 8-bit 2's complement binary form, okay, which represent both negative and positive. If we are talking about an unsigned representation, yes, of course, we can do it, because unsigned representation in that case, my range is from 0 to 255, and this value falls well between those two numbers. Okay. Now question become, how do I do, for example, 42 positive numbers? Okay, so 8-bit, we know range is -128 to 127. We put the indices and then we put a leading 0. Okay, means it's a positive, and then convert as usual if it is within the positive range, which is a positive number and within that range. So we put a leading 0, and rest of the bit we convert as usual. We just look at, okay, this is my decimal position, it is more than the given value, put a 0, then go next. If it is more than or less, no, we put a 1, then subtract that. 42 minus 2 is 32 is 10, then next is 16, no, it's 16 greater than 10, put a 0, 8 less than 10, so I put a 1, subtract, and that becomes 2. 2 less than 0, less than 4, we put a 0, 2 is equals to, we put a 1 there, subtraction is 0, rest of the bits are 0, no problem. So as you convert as usual by putting leading a 0. Now question become, how about your negative number? How do you do it? So for negative number, we do this way. Put a leading one, okay, MSB. Then we compute x as the mod of your absolute value of the lower bound, which is minus 128, and absolute value of the number to be converted. So absolute value of minus 120 is 128, and absolute value of 42 is minus 42 is 42. That is 86, right? Now convert this 86 into the binary for the rest of the bits, which becomes 1 0 1 0 1 1 0. Okay, and your answer become 1 1 0 1 0 1 1 0. So this is your 8-bit 2's complement binary form of the value minus 42. So what do we do? Bottom line, we compute. We need to know the range of this system, and first of all we need to check if this value to be given, value given to be converted, is falling within that range. And then if it is within the range, if it is a negative number, put a leading one, and then compute is lower bound, absolute value lower bound to the absolute value of the number given. You subtract it, whatever subtraction result, it becomes positive, and convert this into rest of the 7 bits as usual. So that's all for this lecture, number representations. If you have questions, please send me emails, or you can ask me in the class.